Welcome to Lecture 5 of Mathematics for Computing Integration. Effective enterprise defense is an architectural challenge. It requires a structured, hierarchical planning framework that maps every security control to a rigorous mathematical model. Today, we will define the specific levels of security planning, analyze the system security plan, and apply mathematical models to evaluate system effectiveness. Subjective administrative documents lack the precision required to evaluate an enterprise-grade defense system. In computer science, if you cannot measure a system's efficacy through objective mathematics, you cannot secure it. Security architecture begins with strategic planning. This sets the overarching direction for the enterprise, typically operating on a long-term scope of up to 5 years. Below that is tactical planning. Over a medium-term horizon of about 1 year, tactical planning focuses entirely on implementing that broader strategy. Finally, operational planning handles the short-term, daily or weekly security activities. These 3 tiers form a strict top-down hierarchy. Every operational task must align with the tactical plan, which in turn must perfectly support the overarching strategy. This diagram shows the 3 tiers mapped in a top-down hierarchical flowchart. Beside it is the governing formula for this hierarchy. System effectiveness equals strategic times tactical times operational. Let us walk through a hypothetical scenario. We will assign the strategic level a high performance score of 0.9. We assign a moderate score of 0.7 to the tactical level, and a weak score of 0.6 to the operational level. Calculating these inputs yields an overall effectiveness score of exactly 0.378. Notice the severe drop in the total score. A 90% strategic success rate is practically neutralized by a 60% operational failure. Because systems dependency relies on a multiplicative model rather than an additive one, your security chain is strictly as strong as its weakest link. Complete operational alignment is paramount. The primary threat to this hierarchical structure is misalignment. Misalignment is the exact mathematical divergence between what is written in policy and what is executed in actual practice. Operationally, this divergence stems from human error, poor communication, a lack of resources, and inconsistent execution of policies. Here we have a deviation analysis graph plotting this discrepancy. The top line represents the planned strategy, and the bottom line represents the actual implementation. We measure this divergence using standard error analysis logic. Misalignment equals the absolute value of planned minus actual. We use the absolute value equation to ensure the gap is measured strictly as a positive magnitude of error. Plugging in the numbers from our previous scenario, we have a planned strategic level of 0.9 and an actual operational implementation of 0.6. The calculation yields a misalignment score of 0.3. Visually, this 0.3 represents the physical delta between the planned and actual lines on our graph. A deviation metric of 0.3 indicates severe operational risk and high systemic misalignment. The central engineering goal of security management is to minimize this mathematical gap to 0. The formal tool used by engineers to combat this misalignment is the System Security Plan, or SSP. The SSP is a centralized document that dictates exactly how security controls are physically implemented within a given system. A valid SSP requires clear system descriptions, comprehensive risk assessments, assigned personnel roles, and strict monitoring procedures. This visualization shows a wireframe SSP document paired with our next metric, the coverage model. The formula reads, coverage equals implemented controls divided by required controls. We utilize this ratio analysis specifically to locate vulnerabilities in the physical architecture. A fully secure, ideal system must achieve a baseline coverage ratio of exactly 1. Consider a test scenario where an enterprise system has 50 theoretically required controls. Now, an audit reveals that only 40 controls have been successfully implemented. Dividing 40 by 50 results in a coverage score of 0.8, or 80%. Any coverage ratio less than 1 mathematically proves the existence of exploitable security gaps within the physical architecture of the system. While the SSP provides a static structural framework, policy management involves the active, unpredictable element of human behavior. The development of any policy starts with identifying requirements, drafting the text, and submitting it for formal review. Once approved, the policy moves into operational execution through implementation, continuous monitoring, and strict enforcement. This circular diagram illustrates these exact steps, forming a continuous policy lifecycle. Constant iteration is required, evaluated by the central formula: compliance rate equals compliant actions divided by total actions. The monitoring phase of the lifecycle feeds data directly into this statistical compliance model. This formula translates human actions into a quantifiable performance metric. If we analyze a server log detailing 100 total user actions over a specific period and filter that log, we might find that only 85 of those actions complied with the SSP. Dividing those numbers yields an 85% compliance rate. A low compliance rate mathematically indicates weak enforcement. The required response is a mandatory return to the drafting phase to fix the policy. This 4-panel digital dashboard displays the complete mathematical architecture we have built today: effectiveness at 0.378, misalignment at 0.3, coverage at 0.8, and a compliance rate of 0.85. Strategic, tactical, and operational planning must maintain strict hierarchical alignment to prevent multiplicative failure across the network. The system's security plan acts as the structural anchor, bridging strategy to physical implementation. Active policies must be continuously monitored, evaluated, and improved based on statistical compliance feedback. Mathematics provides the objective tools required to move cybersecurity from administrative guesswork to rigorous, data-driven defense.